Today I'm going to talk on the developments on hydrogen production schemes. Of course, when we talk hydrogen, we need to talk about the storage and applications of that. But I'm not going to talk that part because the key thing is that we have to first produce the hydrogen. And we'll see how nuclear energy is going to support this program. So I'm going to summarize the actual developments that are happening around the globe, especially large-scale programs. There are, of course, small-scale, production schemes are going on, utilizing nuclear energy. Of course, you can produce it in a number of ways. And this will be specifically addressing those developments that are currently going on and the state of the art. And then, of course, that will help understand what is the status right now in this technology. I'm also partly representing here the Indian Institute of Technology, Jammu, where I'm actually doing my sabbatical work. In fact, we're developing some programs also in this respect. So I would like to acknowledge that. So first again, probably, it's quite spoken here a couple of days on energy. So I'll just again emphasize why we're talking hydrogen here as an energy carrier. So I'd like to bring that context and then give programs that are going on in terms of the technology as well as the implementation of those technology to produce a hydrogen and combine that with the nuclear energy. So there are a couple of things that come in. Of course, the very easiest way to start with for nuclear will be using electricity, which is electrolysis. And also you can do with heat and electricity, that will be the high temperature electrolysis. We'll talk about some advances in that one. And then the other one is the thermochemical water splitting, which uses primarily the heat energy coming from that. Again, as you know that the reactor will be source of heat and electricity in that respect. And then, as we also heard previously, there are advanced reactors that are being developed, specifically the high temperature reactors. And again, in terms of the production for the efficiency, the high temperature makes quite a good sense. Any chemical process, of course. And so we'll bring that out. And specifically, I'll point out some of the initiatives that are going on recently with the Department of Energy from US. So this is, I always bring this up. It's a very, very interesting one. Professor Richard Smalley, Nobel laureate in buckyballs, famous person, visited Purdue. We had invited him. We used to conduct hydrogen symposium those days. This was in 2004. He passed away a few years later of that. So he had actually traveled worldwide after his Nobel Prize winner, very concerned about the energy issues, and collected with the audience, something like this audience, various sectors, different disciplines. He had more than 200,000 inputs. He did a survey and from all kind of industries, student communities, professionals, name it, various sectors. And he had connected 200,000 and said, what are the major global challenges? And he summarized them, came with this list, which tops the energy as the highest one. And he argued that lot of the bottom ones here, the challenges, can be addressed if we address the energy issue, including, the war and other issues, for example, the disturbance going on around the globe. And so, it also recently, the Millennium Project, which a couple of years back was developed, and you can see several of these challenges are basically listed here, though this lists the energy as the topmost in terms of the priorities. And of course, we talk about the energy consumption, we talk about the population. This is what we have a current population, 8 billion, right now, and there is a called worldometer. You can check it every day. The number keeps going up, just like your meter, electrical meter. And then the population is supposed to reach around 10 billion by 2060. And so we are looking for energy need that is going to grow along with that one. So what we are using today, this is what we are consuming on average, around 114 million 821 megawatt hours of energy consumption is used today. And then, of course, these are coming from various sources. If you look From majority of them are from non-renewable, which we already have seen that. And from nuclear, it's of course very, very small. Talk about, few percent of that, out of which 8% is in actually electricity coming from nuclear, but energy-wise is very, very small quantity as it is now. So the important thing is that, of course, there is a plenty of energy that comes from sky. If you look at the number, this is the one that strikes every day. That much energy actually strikes every day from sun. We're not harvesting it very efficiently. So what we have right now, in terms of the nuclear, which is our context down here, so about 10% of clean electricity, that's coming more than 440 reactors operating around the world. This is the current operable reactors, and then there are more constructions going on. We are also have shut down several reactors, 213 reactors. So in terms of the availability, the resources availability, what we have, these are our primary energies, fossil, oil, coal, natural gas, all carbon-based one. Then, of course, solar, we talk nuclear, and then geothermal. These are all what we have as a primary energy. If you look at this, the large brick here is the energy that falls every year on Earth from sun. And then the next one will be this yellow brick, as you can see that. It is the next one as a nuclear energy, and then you have coal. These are all limited quantity. Once you run out of this brick, you're done. And of course, it's still plentiful to use it. Of course, depends on how you use it. Of course, it's going to produce a lot of pollution on that one. And here is what we currently actually use worldwide. As you can see, most of them is dominated by the fossil fuel. Well, we had just recently is COP24, and then we have several environmental global warming summits and going on. Of course, this is well established now. These are 400,000-year-old data collected, and they can clearly see there are a lot of fluctuations in terms of the carbon dioxide buildup, warming up period. However, after 1850 or so, our rate of increase of temperature as well as carbon dioxide buildup is very high. We have exceeded all previous, the maxima that have done fluctuations. And so that's where we are currently. And of course, we have a lot of issues with that in terms of the greenhouse buildup, warming, and other things. So since OPEC, that's early 70s when the embargo came out and everybody saw the crisis, that there are limited resources that are actually geographically located, especially the oil crunch. And people thought about looking different way of securing their energy, domestically produced, possibly domestically produced, and also using a vehicle, energy carrier, which is basically what we look at as hydrogen. And that was basically what was proposed that time. And people looked at producing hydrogen in different fashion. Of course, all these are possible. However, these the two things you can actually use more like a green type, which is electricity and hydrogen. And electricity, of course, we cannot store it. We have to produce it, use it as it happens from various sources. So hydrogen was considered in that sense as a fuel, then we can use it, which can be produced from various sources. And it can be produced from various sources, like I said, again, coming from all these drivers that, of course, environmental issues, again, the energy reserves that we have, consumption in terms of what we are going to use it, and then security for each of the countries, they have, energy security issues, again, being independent from that, and it was considered the best value proposition that can be produced from renewables, of course, that will be the most ideal situation, and then, of course, if as it is currently happening with the fossil, nuclear, these two will be the one that what can drive what you call as a green energy or green hydrogen energy. So in terms of the value, as you can see that this is what you call as the energy intensity of that, energy density, and the energy density versus the power density, or you can say that the hydrogen sits down here as a gas. Of course, you can liquefy it, but if you have got a host of these things here in terms of that, you can use it. So nuclear comes pretty top in that one. As we saw earlier, that the energy density of the hydrogen, nuclear energy is very high, and so that makes pretty good sense in terms of using that thing. So the nuclear with hydrogen makes a nice combination in that respect. We have high energy density nuclear, and then hydrogen is the most ideal energy carrier, so that makes an ideal combinations for that one. And if you look, there is already hydrogen industry existing. There is a large demand for hydrogen. There is a more than 75 million tons pure hydrogen is produced or consumed. And then there are, of course, additional 45 million tons per year as a part gas mix, not pure hydrogen, but with other gases and industrial products. And that is basically about 2.5% of the world energy demand. And we just saw how much we consume each year. Out of which, as you can see, India has about 6 million tons per year consumed, so it's a substantial portion of that. And again, the demand also is increasing. In India, it's about 12 million tons by 2020. So that means you need to catch up by producing more hydrogen to cater all your industries going with that. And the majority of that, if you look at in India, about 3 million tons goes on oil refineries, fertilizer 2.4 million tons, steel and chemical industries 0.6 tons. And of course, there are projections, and this is just a simple projections, but later as you'll see, India is looking to develop quite faster with a GDP growth rate of around 7 right now, which is the highest in the world. And so these industries are going to increase. The steel industry is going to increase. Of course, we need more of these fertilizers and oil to cater all our increasing population as well. And so there are more or less very similar proportion. If you look at the US, how much hydrogen is used in each of sectors, they are more or less very similar to India in terms of the fractions that's being used. So hydrogen can be produced from various ways. Of course, this is conventionally what is currently done by methane reformation, steam methane reformation, SMR is referred as. Again, is basically the 80% what produced right now worldwide, and that's well-known process. And if you see any ammonia plant, there will be a SMR plant next to it. Anywhere you see refineries, there will be a SMR plant next to it. Right? It can also be produced, like I said, by electrolysis, by directly splitting water, but we need a lot of electricity for that. And then, we can do renewable liquid reformation or fermentation. There are a couple of other processes we can actually produce hydrogen-rich gases. Biomass, as of course, is a part of the renewables, and there are several processes you can actually produce a hydrogen. Again, biomass, if it's considering as a renewable, so you can recycle this one. Again, the plants can absorb that CO2 as well. The hydrogen can be produced that way. But again, these are low concentrations in terms of if you're looking at large supply zone. This will be in small supply cases in that case. So there are some other technologies that are being currently pursued, which are that's basically some of them I will address. The high temperature water splitting. The high temperature water splitting you can do directly, like temperature is around say 5,000 Kelvin. You can actually 2,500 Kelvin. You can actually split water into steam and thing, but you need a temperature of that 2,200 degrees Celsius. And then of course there are advanced technologies such as biological water splitting and photoelectrochemical water splitting, and these are in a very, very early stage right now. Again, we don't have the catalyst, we don't have the process that makes it any economical as yet, so a lot of work is going on in those directions as well. So now we have these color maps for hydrogen production, and this is all kind of well established now. The gray ones are basically coming from the fossil fuel. Of course, the clean will be the green one, will be the zero carbon coming out. The blue will be the lower carbon where you actually capture the CO2, and of course this will be really the what you call is a black or brown hydrogen that is coming primarily fossil fuel. And we are basically here, and we'd like to move to these technologies ultimately. And so the transition is to gray to blue, and then ultimately to the green. That's basically what the path will be in terms of the reduction of all these carbon dioxide and other issues. In fact, this is just a recent color coding again. which is existing color, and there are some more adding things. Of course, the pink is our nuclear, and we are not officially producing that in a commercial scale, but I will show you there are small scale effort going on in US. There are 3-4 utilities are actually producing hydrogen with the electrolysis process using actual operating commercial plants. I'll come back to that. That's basically the pink hydrogen. And then there is also another thing that what is called as the available hydrogen in the ground, which comes from reaction with a couple of minerals. The water with a high temperature produces hydrogen, and there are actually deposits found on ground. And there is one country in Africa that actually mines that hydrogen, and that is given a color code gold. But if you actually deliberately induce that reaction and produce hydrogen, it's called orange. So these are what we look at in terms of the color spectra for the hydrogen, which is where it is coming from. So this is the actually paper came early this year, I believe. I should have some reference on that. And that, this is actually came 2023. This is where you can actually mine from the ground. And they think recently the news came in the US, they found a lot of hydrogen actually underground from that one, and that's, I forgot the number actually, but a substantial amount which is economically mineable hydrogen from that. So what I'm trying to explain is that there are a lot of industry existing, and there are a lot of potentials to go to this route of as a hydrogen as the energy carrier. So the nuclear hydrogen production, and when this OPEC program, crisis was there in 1970, when the nuclear was talked about, people also talked about the nuclear hydrogen. NHI started actually in USA in the 1980s, Nuclear Hydrogen Initiative. So a lot of talk has been going on how we can actually produce hydrogen by using nuclear. And so like I said, the way, of course, the product from nuclear reactors are basically electricity and heat. You can use by electrolysis, and if you use a electrolysis process, so overall efficiency, because just to produce electrolysis, we're talking Rankine cycle, which is 33%. So your overall efficiency goes down in terms of that. You may get to maybe 24%, maybe with the high temperature reactors, 36%, right? And then, of course, the advantage with there is that why we are going to produce hydrogen when we have electricity, just use the electricity, right? Of course, if you look at what's called the duck curve, daytime supply electricity is higher, price is higher. Nighttime there is a demand is lower, and the price goes down. So you can play economics a little bit there, use when the electricity price is lower, and produce hydrogen, store it as energy storage. That's one possibility. And that's what some studies are going on right now in a couple of utilities in the United States. There is another technology that I was talking about. This also was developed started in the 70s when looking at this thermochemical water splitting. And you can actually get a quite good high efficiency up to 50% directly using the heat with this one. And these technologies, some of them are at the different stages of maturity, especially sulfur-iodine cycle. We'll talk about that. And that is actually pursued in a number of countries. I'll show some of those developments going on right now. And of course, you can combine heat and electricity, which you can actually do what's called high temperature electrolysis, are using some hybrid cycles where you use heat and electricity. There you can get a pretty high efficiency in that respect. So these are some of the temperature ranges we are talking about. Low temperatures like alkaline, PEM, or those kind of electrolysis processes. Most of the PEM or alkaline are the ones that are used. And then your high temperature electrolysis, solid oxide fuel cell based. Then there are new advanced also made in that, especially the electrolysis cells. And then we talk about the thermochemical cells. And then, in fact, the studies have been conducted. We heard a lot of SMRs today. Of course, there is a lot of efforts going on in developing several advantages coming with the SMRs, like factory actually, and SMRs being shipped and built out. And so if you just use that, of course, even to existing, the steam methane reformation using the reactors, we can actually reduce carbon dioxide emission by 30%, because when you do the steam methane reformation, the 30% of heat energy or the natural gas is actually used to make it, that process going on. So you can at least save that 30% even if you do the SMR process if you use a nuclear heat. So there are some advantages in doing that. So some energetics. So typically, here are some numbers, you can look at that. Typically you need about, if you do the low temperature electrolysis, about 254, 257 kilowatt hour per kg. But most efficient will be around 37, 38 kilowatt hour per kg to produce electricity. And that will be the goal to do in electrolysis to reach that level. So you get a pretty high efficiency in that respect, almost like 80 to 90%. So PEM is well established, process, PEM electrolyzer. And like I said, you can buy them commercially, you can use them electricity. The problem with that, again, we're talking about the efficiency. So like I said, most of the low temperature electrolysis require, substantial more than what is actually required. Theoretically, it will be 37 kilowatt hour per kg of hydrogen. That is the actual amount of energy needed to split water. But you need quite high in that respect. So that's the inefficiency we are talking about this one. These are some of the efforts that are going on the world. I'm just showing the data, what's currently available, using this either electricity-based electrolyzer. So this is the alkaline one. I know there are several efforts that are going on, in the megawatt scale right now. And this is one case that was studied recently. I was a little bit part of this one. So the point I was trying to make it is there that the efforts are done in terms of looking this technology where in electricity price is cheaper. Okay, so if you just have to sell electricity at a cheaper price, then you can use that, and that's where it makes sense. Or if you can produce electricity in cheaper price, you can actually make this technology to produce hydrogen and store it. So some of the characteristics, these are substantially improved over the years. If you look at the current density here, around up to say 0.5, so you are getting about 2 volts or so. That's a pretty high compared to previous data. These are the most recent data that have come up in terms of the efficiency of these alkaline fuel cells. I know there is effort going on in BRC here. I think our next speaker is going to give more highlight on this technology. So the reason for that one is that this is the available technology. You can buy them, and if you have electricity, you can actually produce it hydrogen. It's not necessarily using hydrogen for for other technology. What we already talked about there, it needed for even steel industry, glass industry, and other products where it is very important to have that. And so in that case, you can actually use this one. So I'm just showing some of the recent data coming from that one. Then the solid oxide electrolyzer is very interesting because the efficiencies are very high. You can get up to 80-85% efficiency as compared to 50% just purely by electrolysis processes. And so there's also a lot of simplicity here in terms of the loop. That's for running this one, and so that except that it's of course high temperature. We're talking up to 850 degrees Celsius cell, but the cycle is the loop is very simple as long as you can have a high temperature stack here. So now this makes very interesting. If we have a reactor which can give you high temperature in the order of 500 to 600, 700 degrees Celsius, and of course you can use that with a very little amount of electricity to split water and produce hydrogen. It makes a very good combination to couple that with this process with the nuclear reactor, especially the high temperature nuclear reactor. There are, like I said, there are a couple of industrial demonstrations are going on. This is a 1.1 megawatt SOEC product, and it gives a lot of its characteristics. And here are just the overall efficiency in terms of that. As you can see, the coming from the high temperature versus the low temperature electrolysis. Again, you are going to you are going to save quite a lot of energy in terms of that. And this is basically what this is indicating in terms of the PEM fuel cell or alkaline versus the solid oxide fuel cell. The energy requirements are substantially low. It's almost to the minimum energy required, which is around 37 kilowatt per hour per kg, as versus 50 and more higher for the other fuel cells. So this was a pilot demonstration program. Again, we do not have any commercial such a production facilities purely based on, for commercial supplies. Most of them are a demo like this you are going to see down here. This is one of that demonstrated. And then what is happening now even in high temperature localizers, one of the issue was there is to maintain the loop at around 800 to 850 degrees Celsius. You cannot use a steel material there at that kind of temperature conditions. You have to use a very expensive material. So people are looking in terms of the different kind of low temperature solid oxide fuel cells. They're actually developed, some of them are developed, can operate up to 600 up to 550 degrees Celsius. You can use the steel material for a lot of the components down there. And these are one recent cells that are developed, which is called the proton conducting layers. And these, as opposed to the ion conducting, the oxygen ion conducting, the TSW zirconia. And so these have very good performance now, even though these are not commercially available in terms of that there are manufacturings are there, like, small scale. But ultimately this will also lead to, the technology for electrolysis, high temperature electrolysis, because the temperature operating range temperatures can be quite low, around 600, less than 650 degrees Celsius. That enables the materials that are piping and other things can be used without steel or steel type based material rather than a very expensive material. So these are kind of right now in the R&D type stage, like maybe TR level 5, 6 in that case almost. Getting ready there. Some of the characteristics are shown down here, as you can see, that they show very significant operational characterization up to 500 degrees Celsius, up to 550 will be the most ideal. And this is the temperature can fit most of these newer advanced reactors, liquid cooled, like lead cooled reactors, or high temperature like supercritical reactors. So this is quite a right temperature ranges that were actually there in terms of that. And this is so there is a lot of interest coming in developing this kind of solid oxide fuel cells with proton conducting electrolyte. There is this came just last this year. Actually, they are getting a lot of notoriety. This is they claim it is a vapor electrolyzer based on solid device type electrolyte. Again, its manufacturing is supposed to be, there is actually a patent and a couple of groups are working, I know of. But this is a company, several of BP, Mitsubishi have actually just recently signed contract with them. And they claim up to almost like a theoretical value required to produce a kg of hydrogen, which is 35 kilowatt hour. Most of the technology we saw now with the PEM or alkalines are in the order of 50. And this will be very, very low compared to that one. And so, again, these are the most recent ones that are going on. There is just one company started a couple of years back, and there are a couple of more companies are coming up actually in the US right now. So, the utilities has now actually looking very seriously. The US invested about each of these utilities up to $2 to $3 billion to start these programs. The nighttime electricity price is very, very low. Like I said, I sometimes can go negative than actually the price of electricity in the daytime. And so that time you can utilize it to produce hydrogen. And this is one of the cell actually, I think this is in the Constellation. Yeah, this is in Constellation, a PEM electrolyzer. This is actually stock that was installed 1 megawatt, and they are going to increase to 5 megawatt now. Okay, and that is actually operating since February. So as you can see, so what they did, they wanted to establish a commercial loop where the hydrogen produced here either used in the utility itself. They also need hydrogen in the site, but an excess hydrogen they can actually sell to a buyer there locally for a local industry, and then see what is the economics of investing in this electrolyzer using electricity from the nuclear plant, especially in the night time. And so that economics is going on, and that study is going on with this one. There are a couple of more. These have plans going on. This is with PEM electrolyzer. There is another one that's actually going to be the alkaline electrolyzer based Arizona Public Service Pacific, and they are going to, I think this was like a 5 megawatt, I thought. Yeah. So that was in a 5 megawatt. And then there is this is actually high temperature electrolysis that called Bloom Energy, that they have high temperature solid oxide fuel cell or solid oxide electrolyte cell, and that's actually, this is just being commissioned now, 240 kilowatt as a commercial venture. And then, of course, this one has also a 5 megawatt alkaline electrolyzer. Both are coming in. All these three are coming in 2024. So remember, these are the commercial ventures actually, and they are actually using existing nuclear power plant electricity to demonstrate you can have a sustainable production of hydrogen and storage, and so you can have a business plan based on that one. So these are some of the companies, drivers at least from US, Bloom Company, Ox Energy, and then they have reversible high temperature electrolysis, and these are actually going into high temperature electrolysis business. So this is basically a lot of going on right now. Each of them are signing with the different utilities, with the different contract to see whether they can install, operate. So those kind of activities are going on right now in terms of the nuclear initiative. So US is currently looking at the hydrogen production research and program, wherein combining that with other energy sources such as renewables, which is called Hybrid Energy Laboratory. This is actually established in the Idaho National Laboratory. We just saw earlier what you talked about, the hybrid energy, that basically nuclear combining with other energy sources, preferably the renewables, and catering to the different sources like district heating, or hydrogen production, storage of the energy itself, so all those activities. In fact, there is a lab, it's a very small scale lab in the Idaho National Laboratory, and it's exactly looking at this thing. And actually we did a little bit participate on some of the simulation part of this work, and initially, now actually the lab is built and they want to run it as a closed hybrid system. It's a very small scale, and this is what's going to be in the future. How we can look our hydrogen as a nuclear energy as a multi-portfolio utility system, so that it can do other things, and also get combined with other energy sources like renewables, so that we have a complementary green energy sources doing multiple things, catering chemical industry or storage, those kind of things. So basically this is what is going to come in. So there's a lot of effort going on in that respect as well. So INL worked for a number of years on this one, and right now they have installed a 25 kilowatt a demonstration plant. Again, these are I think one of these Bloom Energy and the other fuel cell energy companies are actually collaborating with them. These are some of the facility I'm just showing you. So there's a lot of brisk effort going on, and again trying to establish the technology itself that can be commercialized in an industrial scale ultimately. Some of the advances going on, like I said, high temperature electrolysis, like I said, they did several years, especially stock development. The problem with most of them are these electrodes, especially the cathode electrode is the issue. The electrolyte is not a problem, it's the cathode electrode that the efficiency keeps going down. There's the electrode catalyst activities keeps going down basically with the time. So a lot of improvements are basically in that direction. And the next technology that I'm going to focus is basically thermochemical water splitting. And this again started in early 70s. And there are several thermochemical processes identified, more than 100, and then they screen them down to some that are more practical, that are feasible, technically feasible. And so some have been identified in that one. And so a couple of them are well known, and I'm going to just highlight those. But then we can categorize them in terms of the single step process, or 2 or 3 or 4 or 5 steps. Single first process will be direct pyrolysis of your water, direct splitting with the high temperature. Then the next one is this one, the 2-step, and then there are a couple of processes are there. This is basically what's called hybrid sulfur-iodine cycle. I'm just showing some of them that have been actually demonstrated and done, but there are several of these kind of things. This is another well-established or matured technology, which is called sulfur-iodine process, where you actually intermediary chemicals here like sulfur, iodine are recycled back, and then water is used as a feed material, and you have H2SO4 and HI acids to make a Bunsen reaction first, and then you have these two acids decompose them, produce hydrogen and oxygen. That's basically what it is. The key thing on this one is that temperature requirement, especially for this one, you need about 850 degrees Celsius is the most efficient way to split sulfuric acid. And of course, this other one, hydrochloric acid, is around 450 or so. Bunsen you can actually generate around 120 degrees Celsius. So this is the most advanced one. There are other cycles like a copper chloride cycle. It's like a 4-step cycle. Canadians have worked some of them, so I'll just highlight that a little later. Again, this only disadvantage is that it cannot be continuous batch because there is a drying process, the powder drying, you have to do that. And so, but it's, they did a lot of effort on that one. That's one of the cycle that is well demonstrated. There are a couple of ways on doing that. One is a 5-step or in a 4-step copper chloride cycle. I just shown them here in that respect. And this was also done what's called the University of Tokyo cycle, UT3, as a calcium bromide cycle. I didn't catch up much, but again, it was a multi-steps. So always this is an issue. When you have a multi-step, you have to handle more piping, fluids, and the reactions do not go completely 100%. You have to series cycle them. So, but again, it also requires up to 700 degrees Celsius. As you can see that the ranges of the temperatures pretty high. So it only makes sense these things can happen if you have high temperature reactors. We had participated with this project. Actually, this was with the CA France, Sandia National Laboratory, General Atomics. So these we had one project. Actually, this is actually loop. I did a little bit work on this one. We had a binary reactor there for the sulfuric acid decomposition. But this was like a completely integrated loop actually that was demonstrated. Again, these efforts have varied. Like this we did in early 2000, but then it went down. So interest keeps changing. But now I think that a lot of efforts are coming and looking at seriously in the hydrogen production. So this is a copper chloride cycle. Canadians have put a lot of efforts on that one. One of the reasons they are looking is because the temperatures up to maximum maybe 520 degrees Celsius, and they are proposing to hopefully build a supercritical water reactor, and that will be in the range of this temperature. And this was also demonstrated for a kind of small scale, almost like an industrial based type design. And you can actually split water using this technology. So this is their plan actually. It's currently going on. As you can see that commercial partners they are actually looking right now, and CNL and provisional government investments are going on in that respect, and they hope to have a pilot plant demonstration by 2024, 2026. Now, when I talked about the height, these are various chemical reactions. As you can see that. So we are looking specifically these reactors, very high temperature reactors going up to 1000 degrees Celsius, the sodium cooled reactors maybe 650 degrees Celsius, gas cooled fast reactors can be a little bit higher, and the molten salt reactor around 650, 700, lead cooled reactors, basically around 650 degrees Celsius. So if you look at that in terms of the temperature ranges, so you can actually get several of these reactions, specifically these SI cycle also you can run if you come close to 650 or so, and that's basically the most done. Of course, UCS cycle we just said, and then there are vanadium chloride, and there are some other ones are also there. But these have been kind of cycles are there, and these are some of the possibilities in terms of the reactors we are talking about. So the high temperature reactor is caught up in this one, and actually people are looking at these. Again, I will show a couple of systems that are actually operating right now in Japan and in China, and they are specifically looking at address the hydrogen production using some of this thermochemical process. So the key thing with this one is that using this trisofuel, a 4-layer coated nuclear fuel material, 0.5 millimeter. And so it's like itself is a small pressure vessel, which you can actually, heat it up to 1600 degrees Celsius without any breach of that one. It's well demonstrated now. There is actually technology to produce it very efficiently. So the trisofuel is the key, especially to make it more safer. And so there are a couple of ways to design it. I think they have here showing that. So either you can make these with a trisofuel, a Febble, it's called a Febble bed modular reactor, or you can just make a pellets and use this graphite matrix. So there are two types of designs. One is the matrix type design, the other one is the Febble type design. And there are actually operating reactors like a HTR-10, which is operating Tsinghua University more than 22 years now, and they are building now 500 megawatt reactors. Actually, construction is going on based on the technology. And in fact, this was hooked up to a direct Brayton cycle, very efficiently operated. And same thing, there is another design, which is of course called a graphite matrix, and that one you actually use pellets, and then you have a coolant flowing through these channels there. And this is the STTR operating right now in Japan, and that's been operating for some times now. They don't operate continuously. The STR-10 operates continuously, by the way. They have not operated continuously, but it's been well demonstrated to operate very, very safely. So these are the two reactors, as mentioned you. As you can see that the HTR-10 did directly connect to a double pipe flow, the heated flow going into that, the Brayton cycle daily running it, and this was demonstrated very well, and it's connected there in actually INET, which is in Tsinghua University campus. So what we are looking now, we are looking to have this high temperature reactor, of course, as a power production, which, is in Brayton cycle may be the adequate, or you can run even Rankine cycle also. However, the temperature is very, very important, and that can drive some chemical processes. And so people are looking how to utilize these high temperature scenario so you can drive chemical companies. And there was a question earlier asking about what is the distance between a high temperature reactor and a commercial plant. In fact, I'm working with the IAEA project. In fact, this is actually in Korea. I was actually studied this very recently, and regulators specifically. So what should be the distance? And so they look at fire propagation, safety, and they're talking about it should be very easy to handle, especially for large-scale reactor within a 0.5 mile exclusion zone, in that distance. Or if you have built a barrier, then it could be even shorter than that one. And if you talk about the no exclusion zone reactors, like micro reactor, you can build next to that. And so there is already experience, like I said, that there are already chemical plants existing next to the nuclear reactor. It's just if the nuclear reactor, had an accident and release, what are the effects rather than chemical plant problem. So it's, and there are actually models people have developed and studied, issue that. So that's may not be any issue at all in that respect. So here are some of the HDR, and this is actually a study done by Japan. This is basically on the SI. So one of the poor efficiencies on the HI decomposition there. So you get almost 30% efficiency. You have to recycle the reactants, and so they have developed this basically what you call as the like a dialysis-based decomposition or separation for the HI decomposition. Some of the data I just want to show there. Now, the hybrid cycle we talked about earlier, that the high temperature reactor has you can run a Brayton cycle, or you can use a process heat, and so it makes quite ideal to penetrate the chemical industry, which we are not doing that with the nuclear reactors. We just produce electricity, sell them electricity. We're not utilizing the heat, and so with high temperature reactors make a sense. And so US has launched several program. One is called the H2 at scale. So now this has translated into what's called the hydrogen hubs. So they actually established 5 hydrogen hubs, and they invested more than each hubs is invested about $1 to $2 billion, and then the industry puts $2 billion, like $2 to $4 billion. There is almost like $40 billion now almost invested in several companies. And so the whole goal is that, and the nuclear is going to be one of the major role. Of course, what the idea in this hub is basically to first establish a infrastructure. We don't have infrastructure for hydrogen. Without infrastructure, we cannot just do things. And so the other fuels are going to be used in that initially, and then ultimately, you can switch it to renewable and nuclear. And this is basically the price cost in that, and it clearly shows these are studies done with steam transformation, wind, and other things. As you can see that the hydrogen or the nuclear looks very, very attractive in that all this respect that was studied. This is for 2035 time frame we are talking about. So there is already a certain infrastructure exists, at least in the US. There are actually 16 hydrogen fueling stations in California only, of course. There are a couple of them in a couple of university campuses. This is to demonstrate that we can have this technology and use it, and these are currently operating. There are some future plants are also going on in terms of the fuel cell and electrolyzer systems in the United States. So currently these are in terms of the legislators or the provisions, that money that government is going to invest it. And the idea is that these are small amount, but right now this is what got invested initially $8 billion, but now it's ballooned into almost like $30 to $40 billion coming from industry as well as from this thing. And so these are the 5 hubs that were established. So I am associated with one of this one, at least from Purdue. But as you can see, not all of them are actually using nuclear energy, of course, So there are 2 of them are actually going to be using at a low cost electricity, basically. That's what I talked earlier, because that's the most practical of using it just to go ahead and produce hydrogen. And so I just wanted to point out that this just came about a month back. These were all announced, and so there will be thing. And the overall they're talking in the next 6 or 7 years, about $300 billion will be invested in hydrogen. Okay, with that, I'd like to thank you all and appreciate it.